multidisciplinary design optimization is that you need to consider many views simultaneously and need to find a solution within, let's say, this conflict of different expectations. And an airplane from a structural perspective may look like this, from an aerodynamicist perspective rather like this, from somebody who's concerned about fuel consumption rather like this, and somebody who likes to fit in as many people as possible would rather look like this. And then, of course, in a multidisciplinary design setting, you want to reconcile those views. So this is the most important thing when you think about multidisciplinary design optimization or in general optimization. That's the interface between the engineer and that machinery that you're going to use. This is the problem statement. And whenever I read a scientific paper or I listen to a talk or somebody presents a design problem to me, then I always wonder, what's the design problem to solve? So even if you do not want to present something about numerical design optimization, you nevertheless want to make clear what problem you're actually trying to solve. And in numerical or multidisciplinary design optimization, that also serves the purpose that you get access to that machinery. And therefore, you want to pay extra attention to making this right. So you typically have an objective function, well, not typically, always have an objective function, which you will use in a design objective that you express. This is the design objective. You want to minimize f of x. You want to be clear about what your degrees of freedom are, what the optimizing procedure can play with. And you want to be very clear about the constraints. And this expression here is an equality constraint. This is an inequality constraint. This is a little redundant, but I mention it nevertheless. That's a design space that you would express using an inequality constraint. And you always want to make sure that you provide this. And I'll show you today an example of what happens if you don't. And another, that's something that is particularly important to me. And I wonder why I often see little attention being paid to it. This is the distinction between a constraint and a constraint function. The constraint is the entire expression, and a constraint can be satisfied as true or false. The constraint function is an ingredient. A constraint function is a mapping from a variable onto another variable. Two different things, but they, of course, have something to do with each other, because in order to express a constraint, you typically need a constraint function. Okay, but please make sure that you distinguish between these two terms. Then let's go through some other terminology. So when we look at a system, we typically look, what we mean by that is a model of a technical product. So like this rod that you exert a force to. And then there are system equations. This is just the math that tells you what it will behave like. And from these system equations, you would extract a system response. You do that by using solvers, or by, you may even, may be able to solve some equation analytically. But the system response is really a full-scale, detailed description of what your model or what your system does. And from that, again, you want to extract your quantities of interest. And this may be here, for example, the deformation of the tip of the rod, as opposed to the entire displacement field. The system response is the entire displacement field, which you need to know in order to solve your system equations. But as a designer, you just want to make sure that the tip of your rod doesn't move too much. And this you would call a quantity of interest. And another quantity of interest may be something that is very easy to compute, something like the mass of your system. Those quantities of interest, they will be typically, they can either be used for your objective function, because you want to maximize or minimize them, or you use them to formulate constraints. And then you need to have your quantities of interest as in a form of a constraint function then you can use it either as for an equality constraint or for an inequality constraint. And you typically want to formulate your inequality constraints such that to bring it to a standard form that it is less or equal to 0. You could have done this here too, but formally this is still correct. An equality constraint, the standard form would have been f of a minus LFEA equals 0, for example. But those are both valid equality or inequality constraints, and then you can also cast it into this compact notation where you can see here's your explanatory variable or degree of freedom, and you have two depending quantities expressed as your objective function or your constraint function. One of them here will be subject to an inequality constraint, and the other one is what you want to minimize. So much about the formalism, and today we will get started with very simple optimization math. It'll be mostly one-dimensional, and much of it you probably have seen, but we will go through it anyway because it'll provide the basis for what we will do in higher dimensions, then starting in lecture 3 and 4. So the theme today is from the engineering problem to the design optimization problem. And we start by looking at a very simple problem. So those of you who are not mechanical engineers, please apologize. I like problems where I can use my intuition. And that's why we will derive very briefly an objective function and also constraint functions from a mechanical model. And the mechanical model is seemingly simple, but already actually quite difficult enough to establish all fundamentals of optimizations on it. So look at this 2-bar truss consisting of 2 rods with joints attached to a wall, and there is a vertical load applied to it. You can, for those who are from aerospace, I think there was one person only, but anyway, also for mechanical engineers, it may be more exciting to think of a bipod. How the satellite structures that they're sometimes supported by bipods, and this is the mechanics that's actually relevant for them. So, and we want to do something with the displacement of that thing, and I can tell you already, we probably want. We want to minimize, we want to build a lightweight structure that is stiff, okay? And we want to find an ideal lightweight structure by using an optimization framework. So possible quantities of interest will be the deflection or the deformation in the vertical direction and the mass of that thing. And our design variables, those variables that we are in control of as designers, will be the cross-sectional area of those 2 rods, A1 and A2. Young's modulus. Actually, you could even say we're using 2 different materials, but now we're using only one material. Yeah? That'd be, say, steel or aluminum. And we have for that material, we have a corresponding density. So these are 2 really design variables that we can modify by changing the material. Then the base length L can be altered, and this angle alpha. All of these variables, and you could think of others. You could also change the profile geometry, but you can make it more complex, which we're not doing here. So we're only considering 6 design variables as candidates, and this is what we'll be working with for the next couple of lectures. All right, so the systems equations tell us that there needs to be an equilibrium, so the balance equations of linear momentum in the xi direction. Actually, xi we introduced because x is already used for our design variables. So rather than x and y, what we're using here will be xi and eta, but it's simply a spatial coordinate. There's nothing fancy about it. So our balance of forces in the horizontal direction here at this node will be this, and the balance of forces in the vertical direction will be this. And from that, 2 equations that you can already use to identify the forces acting in these two rods, S1 and S2, which will depend on the force applied and on the angles. So then we need to plug in the material behavior, which you can express just by Hooke's law. And since we already know the forces, from that we can conclude that the extensions of those rods will be L1 and L2, depending on this expression here with material properties and some trigonometric expressions, and well, mostly our design variables, obviously. All right, so then we need to make sure that those two extensions here of our rods, that they still that these rods are still connected. And so for that, you need to look at the kinematics. And well, I'm not going to go through this here in detail, but the math is presented here on that slide. And then what you can conclude from that is how the system deforms. You could even express what the entire displacement field would be like, but we'll make the step now directly to the quantities of interest. And well, there'll be this. Our displacement will be given as a function of our design variables. And our mass will also be given as a function of our design variables, these two expressions here. And if you don't understand the mechanics, it's not so important. Just make sure that you know what these functions here look like. All right, and now let's go to the first engineering problem. It says find the optimum angle for the best stiffness. That means minimum displacement. So we have one design variable alpha now, and we want to modify it such that it maximizes the stiffness. Everything else will be the same. So Young's modulus, density, everything else will be fixed. We can only play with alpha. And you can imagine if you make alpha very large, you'll make this rod very large. So you'll add a lot of mass. But when you make it too small, you have a very bad angle to support that vertical load, because that'll be supported by moments. So probably the best angle will be somewhere in the middle. All right, so we go from the engineering problem to a very formal problem statement now, which will be f of alpha is this term here. I mean, actually, I forgot to mention one thing. All the other design variables that we're not treating as design variables right now, we set them to some nominal value. Nominal value means it's just some state as a reference state that we will be using. So we will have a force of 1,000 newtons, Young's modulus of steel, 1 meter base length, and a cross-sectional area of 100 square millimeters, something like this. And now let's look at the problem. So we can plug in these numbers, and we get this as an objective function, which has a unit. The unit is, of course, millimeters, and because it's a displacement. And before we start minimizing, though, we may want to look at the response of this thing. I mean, what is f of alpha? What does it look like? And when we do that, we notice, oh, something strange happening here. Really bizarre. And when we set up that problem for the lecture, we said, we made a mistake. And then actually we did make a mistake. I'll show you in a minute. And we said, let's also teach it here in this class, because the mistake we made is, I guess it's a nice mistake to learn from. So, and I'll go through this now. We have a negative displacement here at an angle of larger than 90 degrees. And well, first insight is that, if alpha approaches 90 degrees, something weird happens, because that rod all of a sudden becomes infinitely large. What is that? And of course, that's a mathematical artifact of our model. We set up that model that way, and we should start to wonder, do we have a good model or not? I mean, I guess in theory, you could imagine a rod becoming longer and longer and longer. And you may want to think about treating with this funny setup 90 degrees. But what's also interesting, if you go above 90 degrees, you have a rod going like this. What could that mean physically? Well, physically, it could mean there's a wall attached on the other side where that rod goes to. Interesting, something that you haven't thought of. So one message is actually that when you manage to formalize an engineer's view and put it into formula, you sometimes may get into regions that you haven't anticipated, which may still be valuable for you. You know that other attaching the rod to the other side that maybe, I don't know, perhaps that may also work. Only problem is you have a negative displacement, and that's strange. Why would you have a negative displacement? And I guess the easy way out would be to say, well, that's trigonometry, and let's ignore that. And let's just bound the problem properly and let's move on. Well, but when you carefully think about it, so we made a mistake in our formula. The thing is that, there is this one relation that we used. This is the length of rod 1 related to the base length. So remember, we set up the problem such that the base length was our design variable. We could have also formulated it differently. We could have said L1 is the design variable. And that way entirely changing the dependencies. We could have done that, but we didn't. And so when L1 is the base length and you increase alpha, make it larger and larger, then L1 approaches infinity, obviously. But when you're above 90 degrees, then you can think of it as having this extra wall here. And it doesn't make sense to have a negative length. So you should add an absolute value here in order to correct your model. So once you do that, you have a corrected model that looks like this. And that makes a lot more sense. Okay. And then, of course, you can either run an optimization on model 1 and restrict your design space to a range from 0 to 90 degrees, or you can run an optimization problem from 0 to 360 degrees and leave that open with a fixed model. It will, in the second case, you will end up with 4 optima, which are, of course, academic. The practical optimum probably will be only this or this. Yeah. But then, of course, you could also think of a rod being attached to the wall like this, or being attached to the wall like this. So you have 4 different solutions, and that you would only get when you have a correct model. So the general recommendation, and that's also a little, from my experience, see, when you start that machinery, like I like to call it, you're not operating in the range of intuition anymore. That machinery does something, and you have very little control over what it's doing. So you really want to check your models and make them as plausible as possible. I guess everybody tells you, but you probably, in order to really value that, you have to spend hours looking for the code and then realizing that you should have set up your model more carefully. But perhaps that recommendation now already saves you a couple of hours. As my thesis advisor said, you're much faster walking slowly. So check your model. It saves you a lot of time. And then the next thing is, of course, carefully specify lower and upper bounds, but we'll get to that also in the next slides. So once we fix the model, actually what we did here is we included, we said we're going to restrict our design space to 0 to 90 degrees. And there's one thing missing here, though, because the absolute values we should have in here anyway. Can you just take a brief note for the correction, because the absolute values here are missing? So even if you restrict your model, actually, that's another thing I wanted to mention. If you restrict your design domain and you're safe, you still want to use the fixed model, because if you're working in a team with other people and they don't know that your model only works in that design space, you don't want to leave landmines somewhere hidden in your model. That's why actually there should be absolute values here too. So you'll find out your minimum is here, 60 degrees. And as you know from high school math, the conditions for this being an optimum will be that the slope of your objective function is 0 and the curvature is positive. So that's sufficient and necessary. Actually, this here is the necessary condition, and both together will be the sufficient condition. And that's what we call an interior optimum. I guess you can ask, but I think things are pretty simple so far. All right, now let's look at another unconstrained problem. And let's switch design variables. Let's consider, oh, there are actually comments in the chats. Do you have, so if there are questions, you can, okay. So if we switch design variables, so let's say the angle is fixed. Angle nominal value here now 45 degrees. But now let's think about using more or less material. Then, well, we have the same general objective function, but when we plug in the nominal values, only this remains, 1 over a. And if we do not constrain, if we not use proper bounds, if we do not specify what our design space is, we'll end up with this scenario here. And it'll give us the trivial answer that, well, we can minimize U upon increasing our cross-sectional A further and further and further. And so formally, you could say the solution or the optimum would be at infinity, which I think is not a very meaningful statement. So you might as well also say you don't have a solution. That's equivalent. I mean, it's a useless solution is like no solution. And what you can say is the optimization problem is not well constrained. So something we have mentioned before, that you want to, in order to come up with a meaningful solution, you want to constrain it. And so in that particular case, a meaningful constraint could be, you look at your material storage space and look at the profiles or the rods that you have, and you pick the largest, and that would be your natural constraint that you would use here. So there's another way to constrain it. I mean, you can either constrain your design space directly, or you could constrain the mass used. So that's somewhat implicit. Huh? And because the mass you would have to compute from your cross-sectional area. And well, you could say that there is a design variable A again, your objective function, and now you formulate constraint functions, and we're going to look at it in two ways. We're going to look at it in a with an inequality constraint and with an equality constraint. And for an inequality constraint, you would say, well, I want my total mass not to exceed m naught, or my constraint function, m minus m naught, I don't want this to exceed 0. So that would be the inequality constraint perspective. And here we have the equality constraint perspective, where say, I want my total mass to be exactly m naught. And m naught we set here as 2.86 kilogram. I don't know. I don't remember the reason, but I guess there's because we get a nice number when we do that in the end. And our design space is actually still it's still an unbounded design space. So our design variable going from 0 to infinity. And here are our nominal values and the result. So here's the mathematical formulation. Minimize f of a, design variable a. And here's our constraint function. And the obvious solution we will get will be this. So we'll get stuck at the right boundary. And here it's just important to note that at this constraint, typically our gradient does not vanish. But now we have a well-constrained problem when we have a boundary optimum. Now let's look at the same formalism now with an equality constraint. And so really the equations almost don't change. It's only that we replace the less or equal than 0, replace it by an equal sign. And what we'll end up with is the same solution. It's actually kind of a boring optimization problem because your equality constraint already tells you what's the only feasible solution. And so there's nothing really to minimize. But again, the gradient here does not vanish. And that's an important observation. All right, now let's make things a little more complicated and let's add 2 design variables. So now we consider the cross-sectional areas of both rods independently, A1 and A2. And well, we make that explicit by saying our design variable vector now has 2 components. This is the objective function. And again, we'll look at 2 different treatments. One of them will be a treatment using an inequality constraint, and one of them will be one with an equality constraint. We have an unbound design space, or that's only bound on one side. Here are our nominal values. And now this is the mathematical formulation. And so this is a nice plot that tells us a lot about the optimization problem, unfortunately only in 2 dimensions. But what you see here are the 2 design variables. And each line is a contour line where of equal values of your objective function. Our objective function was u, the displacement, and on this line, your displacement doesn't vary. So the negative gradient of f, so the downhill direction, is also indicated. So when you minimize f, you want to go down this way as far as possible. That's the downhill direction. And this here is the feasible domain. So we have an inequality constraint on the mass, which will tell us that every design in here is good and any design there is bad. And also we have a constraint saying that our cross-sectional areas should be larger than 0. So if you use numerical optimization, actually you can also solve that analytically, then you'll end up with a solution where you have 2 different cross-sectional areas. So our design problem that we looked at before, where we assumed the same cross-sectional areas, is in some sense not optimal. So optimality also defines a lot on, and it depends a lot on the problem statement. And only now that we made both cross-sectional areas available as design as degrees of freedom, we have the means to further improve the current design. So then again, we look at this now from an equality constraint perspective, and this is really only a formal exercise, because again the expressions stay the same except for that equal sign here, for that inequality sign that is replaced now by an equal sign. Important is that now you're only allowed to glide along that green line here. And well, in this particular setting, it does not make a difference, but there are other optimization problems where, of course, it makes a difference. So here you would just end up there and would again have a boundary, obtain a boundary optimum. Which is actually due to the fact that we have this monotonous dependency on cross-sectional areas. Monotonous dependency, if there's always a downhill direction, your optimum will end up at a boundary, and when it ends up at a boundary, then there is no difference between obtaining the solution from a problem statement with an inequality constraint and obtaining the solution from a problem with an equality constraint. So, but this here, sorry, this is a fictitious example. we didn't find an easy way to incorporate that into our into the two-bar truss. But this is a fictitious example. If you had an objective function with a minimum here, then of course the inequality constraint would not be active. Your optimum would be there. And if you treated it, if you had a problem statement with an equality constraint, then you would end up here. So again, this is fictitious. This is not what's happening in the two-bar truss problem. I just wanted to provide an example where it actually makes a difference whether you have equality or inequality constraints. Any questions? Okay, I think we're pretty good on time. Yeah. So now let's look at typical optimization problems. And we like to categorize optimization problems according to these notions. And they will help us to choose an appropriate optimization algorithm. Or they just help us to understand what we can expect from as solution or not. There's an important term which is called well-postness. And well-postness says that a unique solution exists. It's a mathematical term, and I guess from an engineering perspective, it makes sense. Most of the time, it makes sense. So I'm going to give you an example where we have an ill-post problem, this one here, and this is what we looked at this before. This is where you have an unconstrained optimization problem, and regardless of how large you make A, you can always find a better A that provides a better solution for your optimization problem. You could formally say, well, A equals infinity is a solution, but then that's not permitted here. So that's why you don't have a solution that exists. So then there is another way to look at it. You may remember the difference between closed and open intervals. So an open interval is one that does not include its own boundary. So if you had an optimization problem where you wanted to find the minimum here on this function, and the boundary is not included, then regardless of what solution is proposed, you will always find something that is a little smaller. So also in that sense, no solution exists, and the problem is not well posed. So typically in engineering practice, you do not distinguish between open and closed sets. That's why this is a little academic here. But of course, what you may end up doing is forgetting that there needs to be a bound on a variable in order to come up with a meaningful solution. So it's like doing lightweight design and not imposing a constraint on the functionality of your component. What you'll end up with is a component with zero mass. So and that's just a remark that says make sure that you solve the right problem. But again, just make sure that this really expresses what you want to solve. So then one important property is linearity. And there are actually two types of linearity. So the strict mathematical definition of linearity is this. You've seen this, meaning that if a function f of alpha times x1 plus beta times x2 is always alpha times f of x1 plus beta times f of x2, then this function is linear. That's a strict version of linear. However, we like to call objective functions that look like this also a linear function. And the mathematicians, well, I'm not a mathematician, but and I learned this expression quite late actually, but they call these functions affine functions. And Well, in this case, it just means you add a constant. So a linear function plus a constant is an affine function. And for our purposes, it's fully okay to call both a linear function. Good. So it's important to distinguish between linearity of your objective function and linearity of your problem, because you may have a linear objective function, which you can identify here in this plot by lines representing the linear contour lines of your objective function. And when you have a linear constraint function, meaning you have a linear constraint, then your problem is linear. And then there are algorithms for linear optimization problems. So when you have a linear objective function and you have nonlinear constraints like this, you have a nonlinear optimization problem. And as you can see here, again, we're going downhill this direction. So your utopia point may be somewhere there. But you have a local optimum here and a local optimum there. Multiple optima, which you don't have in linear problems. And so this is a nonlinear optimization problem, although you have a linear objective function. And then obviously, if you have a nonlinear objective function, linear constraints, your problem is nonlinear. And if both is nonlinear, then of course also your problem will be nonlinear. So there's another aspect or another important note on linearity. You may have perfectly linear system equations and a perfectly linear system response, however, have a nonlinear optimization problem. Because when you talk about linear problems in technical mechanics, what you mean is that your solution your system equations are linear. And so here, the two-bar truss problem may have a nonlinear dependency, or the objective function in your two-bar truss problem may have a nonlinear dependency on your design variable. So linear mechanics may still lead to nonlinear optimization problems, and vice versa, actually. Another important property is convexity. Convexity of an objective function and, well, some conditions also on the constraints, which I'll talk about in a second, they will guarantee that the optimum that you found, that the local optimum is your global optimum. And if you do not satisfy this property, then you may have a bunch of local optima. Convexity means that you can connect any, well, is there a graph here? No, it's not. But any 2 points that you connect here in this graph will give you a line which runs entirely above the remaining graph. And you can easily extend that to higher dimensions. So this would apply to arbitrary dimensions. So every function is convex if for 2 points, every 2 points, the connecting line lines above its graph. An optimization problem is said to be convex when the objective function is convex, the inequality constraint functions are convex, and the equality constraint functions are. Oh wait, wait. Affine or convex? I think this is wrong, right? I mean, technically, that can be convex. Okay, but the equality has to be affine, yes. Okay. Yes, I mean, you can imagine if you have a convex function, if your constraint function was not convex, you'd have a similar situation like this here, where we generate local optima by having nasty constraint functions. And as I mentioned earlier, for convex problems, the global minimum is equal the global minimum. Yes, how nice is that? No, it should be the local minimum, of course. Yeah, we need to correct that. So actually, this global optimality business is something I'd like to briefly comment on. I mean, it's nice to know that you don't need to keep on looking. That's nice. So it's let's say when you spend a significant amount of time on solving a problem, and you want to make sure that you really cannot improve, then convexity is that'll tell you, yes, once you have, the gradients are zero, and then you're done. And you also need sufficient conditions to be satisfied, which we'll talk about in lecture 4. That's nice. But very often, my impression was that people are obsessed with this idea of global optimality, sometimes when it's not practically relevant. From a designer's perspective, you just want to get the best you can get within your available means. And whether you got the global optimum or not often really doesn't matter. I mean, it's only valuable to know that it's not necessary to invest more time. I mean, that's nice. But other than that, global optimality doesn't have a value per se. I mean, this is it's a very important and nice concept, but it does not provide, it doesn't improve the product quality necessarily, because if you don't know where it is, you can't use it. Okay, so let me move on with monotonicity. Monotonicity is also a nice property, which is different from convexity. Something can be, monotonically increasing means that, and you can also define that in a multidimensional setting, just means that you're monotonically increasing in a set of variables whenever you increase one design variable out of the set, that's sufficient for your function value to increase. So this is, it's different from convexity and linearity, obviously, and it's a helpful property. And if you're monotonous, then you'll end up on the boundary somewhere. When you're strictly monotonous, of course. And the same thing, yes, there's strict monotonicity, and there's strong and weak monotonicity, and they only differ by having a greater or equal or a greater than sign. And whenever you are linear, then you are also monotonous. Monotonous functions actually are quite ubiquitous. So mass is monotonous so when you think of a system mass of many components, then it's monotonous in the component masses. And or cost is monotonous in the costs of subsystems, or stiffness typically. So whenever you make something stiffer locally, it'll improve global stiffness. So and then it would be stupid, for example, to expect an interior optimum. Then and when you have monotonous influences, then it's all about defining your constraints properly, because you will end up with a boundary optimum. Yes, please. There's a question in the chat. Yes. No. Thank you for that question. Very important question. Let me rephrase it to make sure that I understood it correctly. The question is, why can you end up with nonlinear optimization problems for linear structures? Is it because we made some approximation And it's not because we made some approximation. That's very important. So linearity, when you say something is linear, you always need to be very specific about what is linear. And when you are dealing with linear mechanics, what people say is we are linear. For example, the displacement as a function of f is a linear function. So when I double my force, I will end up with a double displacement. That's a linear response. And that's based on the fact that we have linear material laws. So sigma equals E times epsilon. When I double my strain, I'll get double the stress. It's a linear equation. We combine that with linear kinematics. Linear kinematics means, in that case, when I change my extension of rod 2 by 30%, there will be a change of U by 30%. Okay? So linear kinematics, linear material equations, meaning that'll all lead to the linear response of U as a function of F. If I double my F, I will double my U. But when I make a statement about my optimization problem, I'm not talking about the relation between force and displacement. I'm talking about a different dependency. I'm talking about the dependency on my design variable, which is alpha. And alpha, in that statement about linear mechanics, was always kept constant. Nobody ever said that we are linear with respect to alpha. But this is what is relevant for my optimization problem. Actually, in some sense, I guess this is something, that's really a different view. This is the view of solving model equations of a system that you don't change. And when you adopt this view here, it's all about changing the system. And these dependencies are different. Here you have nonlinear dependencies that all of a sudden become relevant. You had them in here too, but you always kept your angle constant, so you wouldn't notice. I hope that answers the question. So remember, nonlinear problems from linear mechanics. Okay, thank you. There's another question here. Okay, the question is that similar to saying if there's a function that is linear? Well, actually, a linear function has always a constant derivative. Yeah. So there you're only talking about one function. What I'm talking about here is changing your explanatory variables. When you talk about linearity here on the left side, your explanatory variables are, when you say, let me just. So this is the scope. Sigma equals Young's modulus times epsilon. You're linear in epsilon. Yeah? And if you say, I don't know, U is a function of alpha, then you're just not linear in alpha because you have all these cosine, sine expressions, and so on. So that has not. So you're changing functions. Now this is a different function. Actually, I could also say. So this is function 1 of alpha. I could define another function, f2 of f. So in here, we are perfectly linear because this would be 1 over stiffness of the entire structure times f. And k is again a function of alpha, which is built in here. And that, would make that thing nonlinear. I guess mathematically, it's really super trivial. It's just that you're so used to doing linear mechanics where the variables, the explanatory variables that we would look at were always of the same kind. And they were rarely those that we would use as a design variable. Okay, was there another question in the chat? Okay. Any other questions here? I think this is where we stopped. Yes. Okay. Then important distinction: discrete and continuous optimization problems. So the algorithms we teach here are mostly for continuous design problems, or let's say for design problems with continuous design spaces. So if you remember the little design problem where we ended up here, boundary optimum, that was the two-bar truss with the two cross-sectional areas as design variables. So if you have to choose from a discrete set, and which actually is rather the what do you call that? Die Regel, which is the usual rather than the exception, is because when you so when you design something, you would have to buy your ingredients. You would have to buy your rods, and typically they won't make them accurately up to 3 points behind the comma. They wouldn't. You couldn't order a metal profile of diameter 3.176 millimeters. They would only sell you one for 1 millimeter, for 2 millimeters, or for 3 millimeters diameter. And so this is in some sense more realistic. However, this is much easier to deal with. And I mean, if you have to consider discrete optima or discrete design spaces, you may not get what the solution for your continuous problem would be. Yeah? But then, actually, this only is not. We should correct this because we also briefly talk about evolutionary algorithms, and there and those you can use very well for discrete design optimization. But most of our focus is based on this, because in continuous spaces, you have this great advantage that you can compute gradients, and gradients they give you the direction of improvement. That's very helpful. I mean, you can of course approximate them here, and but so this is really nicer for us, although this may often be more relevant. But then again, you can often treat discrete problems just as continuous problems. So, and then also important, there are problems where you can write down the system response in closed form, and this is very rare that you can do that. Very typical is that you have solvers or algorithms that you provide with some input, and they will give you some response, and you don't really know what's going on in here. And most algorithms they need not only the output but also the gradient at a certain position. Then you need to compute that extra, or if you're lucky enough, then that black box solver will also provide you with the gradient. So yeah, we call that closed form solution versus numerical results. I guess that's it for today. Any questions? Today was rather short. Okay, I'll stick around for a couple of minutes. And yes, please. Yes. Say that again, please. When you no, I guess no. What I said is that when you do technical mechanics modeling, you would typically not think about varying alpha. You're interested in computing the deflection for one particular setup. I'm not sure if I draw this the last time. It's one of my favorite things to draw. Did I draw this the last time, lecture 1? I did. So okay, it's going this way. Huh? So alpha is given, but we want to go the other way around. So I mean, for the design problem. Okay. All right. I guess that's it for. Oh, there's another question. Yes. when the curvature is left. Oh, no, convex. Okay, no, that you would call differently. Convex always means that you have positive curvature. Yes. Oh, you mean what are these functions called? That you would call it non-convex. I guess you could also call it concave, but I'm not sure if there may be. I only know convexity as a established term. Concavity you could probably define just, with the opposite signs, but I'm not sure if that's really strictly formalized. Oh, no, that's not the reason for that. I mean, in optimization, they always, or in general in math, they would always try to, they treat these problems equivalently, but you can easily turn this into this by adding a minus sign. Yeah, so that's actually, we do that in lecture 4. You reduce your problems to a standard form, and then you develop all the math for that standard form, and all problems that are structurally the same but can be turned into this, they will be just modified. Therefore, nobody talks about concavity as an important property, because you could have done the same thing for concavity, but people just use convexity. Yeah. There's another question in the chat. No. Guys, I think you got it. I'm really surprised this time, this linearity business, that really made an impression on you. It's not such a big deal. It's not about turning something non-linear into something linear. It's just I'm looking at two different variables. There's no transformation that needs to be done or could possibly help you. It's just, actually, no, I'm going to write this here again. If you have U is a function of many, many things, but now let me just say F and alpha, okay? The dependency on alpha is nonlinear. The dependency on F is linear. That's it. And if I do when I say I'm using linear mechanics, I make the statement about this dependency. And when I'm saying I have a nonlinear optimization problem, I'm making a statement about this dependency. That's it. Yeah. In the end, it's really only about what's the scope of what you're looking at. And when you talk about I have a linear problem, technical mechanics, then the dependency on alpha doesn't play a role. That's the only thing. It's not a big of a deal. Huh? And technical mechanics, technical mechanicists, they say I have a linear problem when their material laws are linear and when their kinematics is linear. That's for them enough to say, I have a linear problem. That's it. Okay, I'll be here for further questions. I say goodbye and I see you actually in 2 weeks from now. Because next time we won't have a lecture. I'll be gone. And yes, in 2 weeks from now. Bye-bye. So actually, I can take more questions from the chats if you want. So I'll be happy to answer them. So just turn on the chat here, or how does? Yes, please.